Okay, Assalamualaikum warahmatullahi wabarakatuh. For this lecture, we are going to start a new chapter, which is on the structural steel column design. Okay, so for this topic, we are going to divide into two parts. The first part is on the classification of the column, and then the second part is on the checking of the column. Okay, so the cost outcome is lies with CO1, CO2, and CO3, and addressing PO2, PO3, and also PO4. The learning outcomes at the end of this topic, you should be able to explain the failure mode of compression member, and also you need to analyze and design concentrated loaded column. Okay, so what is a steel column? Since column is a vertical member that carry axial compression loads, due to their slender nature, they are prone to buckling. And a column may fail due to local buckling, yielding, or overall buckling. Local buckling is actually a buckling mode that occur only at the flange of the column or at the web of the column. But for overall buckling, the buckling is occurring for the whole column, the whole section of the column. They may be buckling in plane buckling or out of plane buckling. But for yielding, failure due to yielding is when the load applied is exceeding the maximum capacity of the column. Okay, so here one example of how does the column looks like in buckling. For example, let's say we have flexural buckling. This is the left one, what we call as in-plane buckling, because the buckling mode is in the axis of the column. Okay, so here is the sectional view. So we can see here the column is still in the shape. The shape does not change. But for out of buckling, so the column is actually rotate. So the axis is changed. Okay, alright. So next. Okay, so this is the types of column that we have. So we have circular hollow section, rectangular hollow section, and hard roll hinge section, and also welded section. For hard roll section, this one is actually similar to I-beam. It's just that for column, they have a longer flange, so that we call it as hinge section. And for your syllabus, we are going to cover on the design checking of hinge column. Okay, so here is design procedure. So for today's lecture, we are going to cover step number 1, number 2, and step number 3. Okay, first of all, we need to identify what is the total axial forces acting on the column. So you need to look into loading on column. So here are some of the loading that you need to consider in column design. For example, let's say you have wind load, roof loading, floor loading, and also wall loading. Okay, for loading on column, axial loads is actually taken from the load transfer from the beam. For example, let's say we have column A is located at the internal span. It is supporting 4 beams at each side. So you have to transfer the shear force from each beam total all to become the total axial force on column. Okay, so you need to add what is the shear force from beam here, 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 and here. The total up, then you get your total axial force on column A. This is what we call as axial load. And also we have unsymmetrical loads for column B and column C. So we need to take the beam reaction and total up so that you get your NED value. Okay, so next is the selection of the section if size is not given. So let's say you have NED and you would like to suggest what is the size of the column that you are going to use. Okay, since we have NED, so this is the equation actually taken from compression check of column. So we modify or rearrange again the equation to get what is the A as required or area required if we are using our NED value. And Fy is actually the steel yield strength of the section. So depending on the steel grade that you use. Okay, so you can refer to table 3.1 in the appendix to get what is the Fy value for each type of steel grade. Okay, from this equation, you calculate NED times Fy value divided by gamma m naught. Okay, so NED here, since normally axial load is taken in the unit of kilonewton. So for here, you need to convert the unit to Newton. Okay, so that the A required, AS required is in the unit of millimeter squared. Okay, so based on the required area, choose UKC size. So the UKC size, the appendix that you are going to use is on the last page of your appendix, appendix B8 and also appendix B9. Okay, the selected size should have the area greater than the required area here. Okay, so the area of section is actually in appendix B9. Column, the last column, the unit here is in centimeter squared. But just now we calculate in millimeter squared. So you have to convert the unit from millimeter squared to centimeter squared. Then you can choose what is the designated size that you are going to use. And you need to make sure that the area must be greater than AS required. Alright, so next, once we get our section size, then we have to classify the column. Local buckling can be controlled by section classification, with the least section being class 3. So it means that for internal compression or for web, the ratio should be less or equals to 42 epsilon. And also for flange, the ratio should be less than 14 epsilon, so that we can avoid local buckling on the column. For classification of column, we are using the same table for classification of beam, which is table 5.2. For sheet 1 of 3 is for web classification. We are going to use this shape for roll section. And since we are designing column is subjected to compression, so you have to use the equation for part subject to compression. So for column, the ratio of C over T must be less or equals to 33 epsilon if the column is class 1. Or for class 2, in between 33 to 38 epsilon, then it becomes class 2. And for class 3, the column should not be exceeding 42 epsilon. And epsilon equation is here, which is the square root of 235 divided by Fy value. Okay, so then we can classify our column, overall column classification, whether it class 1, class 2 or class 3. You need to avoid class 4 so that we can avoid local buckling. And for flange classification, since here is part subject to compression, so you are going to use similar section for flange classification, which is ratio for class 1 is 9 epsilon and ratio for class 3 is less than 14 epsilon. Alright, so that's all for today's lecture. We are going to continue on this topic for next class. Alright, thank you very much.